You will find Walterscheid PTO drive shafts wherever efficient agriculture is practiced. Today, modern agricultural technology would grind to a halt without PTO drive shafts. PTO drive shafts serve to transmit power between tractor and implement and within the implement. In the past, agriculture could only be practiced and food only produced with the help of draft animals and strenuous manual labour. The invention of the steam engine and later the farm tractor heralded the start of the revolutionary development of modern agriculture. For many years, driveline engineering was the domain of flat belts and chain drives. They offered the only possibility for transmitting high powers to thrashers and stationary machines. A further stage in agricultural driveline engineering was the development of the PTO drive in tractors. This enabled the expedient combination of tractive power and PTO shaft power for the first time. Today, the PTO drive shaft is an essential component in modern agricultural technology, and almost all operations would be inconceivable without it. In order to use cardan or hooks PTO drive shafts of the kind typically used in agriculture, a knowledge of the theoretical principles involved is absolutely necessary. Drive shafts follow certain laws when transmitting the rotary motion. They only transmit the rotary motion uniformly when straight. No lead or lag angles occur in this context. The black and white disc fitted for illustration purposes displays uniform rotary motion. When angled, the shaft transmits the rotary motion unevenly as the working angle increases. A lead or lag angle occurs in the driven joint. Here, the working angle is 15 degrees. The velocity variation is 7%. The velocity variation is virtually undetectable on the black and white disc and only has a negligible influence on the driveline components of the tractor and the implement. At a working angle of 30 degrees, as seen here, the velocity variation of the rotary motion is already 30%. Lead and lag angles of the driven joint are clearly recognizable as oscillations in the graph. The non-uniform rotary motion can now also easily be seen on the black and white disc. Premature wear of drive components can be expected. At a working angle of 45 degrees, the velocity variation increases to 70%. The pronounced oscillations of the lead and lag angles can be seen in the graph. The black and white disc rotates extremely unevenly. The destruction of drive elements is the aftermath. The prerequisite for uniform rotary motion with a PTO drive shaft is that both outer yokes and both inner yokes are in one plane. With Walterscheid telescoping profiles, this prerequisite is always fulfilled. Any other arrangement of the joints in relation to one another is wrong and leads to non-uniform rotary motion at working angles. The velocity variation of the rotary motion is compensated for when the working angles of the two joints are equal. This is the case with the so-called Z-bend, when the center lines of the PTO and PIC shafts are parallel to one another. Typical applications for the Z-bend are PTO-driven three-point implements. On these implements, the PTO and PIC shafts must lie parallel to one another in order to achieve uniform rotary motion through identical working angles of the joints. In the case of optimum three-point attachment, the PTO and PIC shafts remain in a Z-bend even when the implement is lifted. In this way, the rotary motion is always transmitted uniformly. With the help of Walterscheid's own computation programs, the optimum kinematics between tractor and implement can be calculated as early as in the design phase. In the diagram, lifting of the implement in millimeters is shown on the x-axis and the velocity variation in percent on the y-axis. With optimum attachment, the velocity variation during lifting of the implement is below 7%. In the case of faulty attachment, for example excessively short and excessively high attachment of the top link, an exact Z-bend is no longer possible during lifting of the implement. 7% velocity variation, which can be considered as the damage limit at a PTO shaft speed of 540 RPM, is already exceeded after lifting the implement slightly. Even when idling, the audible pronounced velocity variation leads to extreme oscillations and thus to wear on the drive elements. Connecting profiles and gear teeth are destined to premature failure. It's absolutely imperative to note that as working angles increase, even small angular differences lead to considerable velocity variation. Correctly attached three-point implements are parallel during lifting and can thus be driven with the PTO shaft engaged, even when turning. In the case of the so-called W-bend, too, where the imaginary extensions of the connecting shafts intersect exactly between the joints, the velocity variation is compensated for by the equally large working angles. Typical uses are trailed implements attached via a long drawbar hitch or tractor drawbar, such as balers, trailed forage harvesters, and trailed swathers. When attached correctly, extreme corners can be taken without velocity variation. Together with the drawbar coupling point, the extension of the PTO and PIC forms an intersection. Thus, the working angles of the joints are equal in every position when cornering. The computer calculation shows that right and left-hand corners can be taken with ease. It should be noted, with this manner of attachment, that the implement must be very carefully matched to the different types of tractor. Matching to the different PTO shaft heights and the varying implement coupling points is absolutely necessary. Using a drawbar of adjustable length, the implement coupling point can be located in the middle between the joints of the main PTO drive shaft. The height must be matched due to the fact that a combination of W-bend and Z-bend leads to spatially uncompensated joint working angles. In the event of incorrectly matched implements, cornering without velocity variation is impossible, as shown by the calculation. In order to avoid oscillations in the case of unilaterally angled PTO drive shafts, a constant velocity joint must be used. The Walterscheid 80-degree wide-angle constant velocity joint transmits a uniform rotary motion over the entire swivel range. The wide-angle constant velocity joint is a centered double joint. As with the W bend, the center lines of the PTO and PIC yokes intersect exactly between the joints. The centering system divides the total working angle evenly. Thus, uniform rotary motion is always guaranteed. WWE PTO drive shafts, where only the wide-angle constant velocity joint is angled, are used on trailed implements which are connected to the tractor via a short hitch or upper hitch. The wide-angle constant velocity joint on the tractor side, shown here without its guard for demonstration purposes, is located either above or below the implement coupling point. If attached accurately, the simple joint is straight and only the wide-angle constant velocity joint aligned with the coupling point is angled. Corners can be taken easily with the PTO shaft switched on. In the case of the short hitch, such corners can only be taken with a wide-angle constant velocity joint. In this instance, a simple joint would lead to pronounced velocity variations and oscillations, and thus to wear and destruction of drive elements. Even slight attaching errors, such as an excessively long drawbar, have only little influence on the drive. Slightly limited cornering is still possible with the PTO shaft switched on. A WWZ PTO drive shaft with two wide-angle constant velocity joints is necessary wherever the joints on both the tractor side and the implement side are angled and neither a Z bend nor a W bend is possible. With loading or silo trucks, the joint on the implement side is also angled, by operating the articulated drawbar for example, so that uniform rotary motion on the clamp silo is only possible with WWZ PTO drive shafts. Attention must be paid to the fact that wide-angle constant velocity joints must not be angled by more than 25-degree continuous operation, as this wears the centering system. 80-degree working angles are possible for short times, for example when cornering, and then present no problems. When providing power via universal joints, additional forces occur which subject the connecting shafts to bending stresses. These additional forces are dependent on the size of the working angle, the incoming torque, and the rotary position of the joint. The additional forces on the end yoke reach a maximum at a defined rotary angle of 0 degrees or 180 degrees. At increasing rotary angles, these forces decrease to 0, while the forces on the inboard yoke increase and reach their maximum at a rotary angle position of 90 degrees or 270 degrees. Thus, the additional forces are not constant, but fluctuate periodically twice per revolution. The knowledge of these relationships is important for the design of connecting shafts and the dimensioning of bearings of downstream gearboxes. because it's here that the so-called idling bending moments must be absorbed. The maximum bending moments, MB1 for the rotary angle position 0 degrees and 180 degrees, as well as MB2 for the rotary angle position 90 degrees and 270 degrees, are calculated from the incoming torque, M1, and the joint working angle, alpha. Mastering these theoretical principles is the prerequisite for precise and practical design of a complete driveline system, in which all drive components are matched to one another. The Walterscheid driveline system. Complete drive systems from a single source. System solutions are our forte. Walterscheid has special drive solutions for the most diverse machine concepts. Walterscheid has branches wherever its customers are, across the whole world. A well-assorted stock of original spare parts for PTO drive shafts, PTO drive shaft guards, overload and overrunning clutches guarantees rapid supplies round the clock. After all, only original Walterscheid spare parts guarantee the function of your PTO drive shafts. Therefore, always look out for this sign. Only use original spare parts from Walterscheid.